Hi everybody, welcome to our first video on trigonometric substitution. In this video we're going to show how to find antiderivatives of functions like this, which don't appear to have anything to do with trigonometry, but yet using trig functions is going to give us a really nice shortcut to their solution. Alright, let's begin. So, I'm trying to find an antiderivative of x squared over root 9 minus x squared. And I'm going to make a substitution. It's going to seem like magic at the beginning, but I'll explain where it comes from. So, here's the substitution. I'm going to replace my x with 3 sine of theta. Okay, we're already getting the trig involved here. Okay, let's see. If I have my x equals 3 sine theta, when I do a substitution, I better figure out my dx. So let's see. dx is, I need the derivative. That'll be 3 cosine of theta, d theta. Fine. All right, now I want to substitute this into this function. Fine. If I replace x squared by, well, let's see, x is 3 sine theta, so x squared is 9 sine squared. So I have 9 sine squared theta over the square root of 9 minus, well, again, I have x squared, so 9 sine squared theta. Then I have my dx. Don't forget the dx. dx is 3 cosine of theta d theta. So 3 cosine of theta d theta. All right, now everything is rewritten in terms of thetas. So there's a chance we could solve this, but it looks horribly complicated. But, something very nice is going on. Let's factor a 9 out of this 9 minus 9 sine squared. So this becomes 9 times 1 minus sine squared theta. 1 minus sine squared theta. Oh, we've seen that before. Yes, with our Pythagorean identity. 1 minus sine squared theta is our cosine squared theta. So this becomes 9 cosine squared theta. And we're really, really happy about that because there's a square root and you have a square. 9 cosine squared, you can take a square root of that, no problem. Okay, let's see what we get. Okay, I'll keep a 9 sine squared theta on top. On the bottom, I take a square root of 9 cosine squared. It just becomes 3 cosine of theta. 3 cosine of theta. 3 cosine of theta. I've seen that before. Where did we see that? Oh, yes, that's right. That was our dx. Haha. Let's copy it down. 3 cosine of theta d theta. We only copy it down long enough so that we can remember we're going to get to cancel those. All right, so moving over here, let's see. I still have an integral. The 3 cosine theta, they're going to cancel. I have a 9. I might as well just pull that out. I have a sine squared theta, and all I'm left with is a d theta. And this is an integral that we've solved before, right? We were able to solve it using a trigonometric integral identity. We were able to solve it using integration by parts. Doesn't matter which method we use, we have some solution now. This will end up being 9 halves theta minus sine of theta cosine of theta. And we're done, right? Well, yes and no. We found an antiderivative. Why are we not completely happy? Well, we started with a function of x, and we finished with a function of theta. Ideally, we'd finish with another function of x. Okay, well, it just means we need to back substitute, right? Well, we didn't substitute the way we're used to substituting, where we would say u equals some function of x. Now the x is written in terms of the theta. So we're going to have to solve for theta. All right, let's move this over to this side of the board, clean this off a little bit, and try this step 2 again. All right, so before we finish with that antiderivative, we're going to have to talk about some trigonometry. So remember, a trig function takes angles and turns them into numbers. For example, the sine function takes the angle 30 degrees and turns it into the number 1/2. Then we also have inverse trig functions, arcsine, arccosine, etc. And they do the reverse. They take numbers and turn them into angles. So for example, the arcsine of the number 1/2 equals the angle 30 degrees. Okay, so that's the connection between these two. Now let's draw a right triangle. So there's my right angle, and there's some angle, we'll call it theta. Now, once I have an angle, then I know that it must be the inverse trig of some number. So let's say that this was the inverse, let's say arc cosine of, well, some number. Let's say 4 over 5. Okay, so I'd like to understand some properties about this angle theta that I get. So the arc cosine of 4 over 5. What is the defining property of this angle? And, well, because inverse trig and trig functions are defined to be inverses of each other, it means that when I apply the arc cosine, if I then applied the cosine to whatever this angle is, I should get back the original number 4/5. Okay, so whatever this angle theta is, when I apply cosine to it, I get 4 over 5. Now, in a right triangle, the way we normally computed the cosine was by taking the adjacent side over the hypotenuse. So in this case, I would want the adjacent over the hypotenuse to be 4 over 5, because the cosine of this angle is 4 over 5. Okay, well, there's a really easy way to make that happen. I'll assign the adjacent side the number 4, and the hypotenuse the number 5. Okay, now I have a right triangle, and I know 2 of the sides, one of the legs and the hypotenuse. I can use the Pythagorean theorem to get the third side. Okay, fine. Let's see, 5 squared is 25, minus 4 squared is 16. Let's see, so 25 minus 16 is 9, square root of 9 is 3. Oh, it's a 3, 4, 5 right triangle. Cool. Now, once I know this third side, I can play a really cool trick. I can now, instead of just applying cosine to this angle theta, I can apply any of the other trig functions. Well, let's try. What if I wanted to know the sine of the arc cosine of 4/5? Well, I just need the sine of this angle. The sine is the opposite over the hypotenuse. The opposite is 3. The hypotenuse is 5. So the sine of the arc cosine of 4/5 is 3/5. Let's pick another one. Yes, you over there. Cotangent. Okay, yes, we can do the cotangent. The cotangent of the arc cosine of 4 over 5, well, we just need to know how to find the cotangent of an angle. Let's see, cotangent is 1 over tangent. So tangent is the opposite over the adjacent. So cotangent must be the reciprocal, the adjacent over the opposite. So 4 over 3. So we can use this in order to find all sorts of trig functions of this angle defined in terms of an inverse trig function. Right? Wouldn't matter. We could do tangent, secant, cosecant, doesn't matter. We can just, once we know these 3 sides, compute all those values. Okay, now we're going to try it where instead of having just a very obvious number here, we're going to use a variable. Okay, so what if we knew that this was the arc sine of some number, and that number, though, had a variable in it? Like maybe, let's say like x over 5. In this case, well, we know that the sine of the arc sine of x over 5 will equal x over 5. Okay, so I'll always start by writing down whatever arc function I've been given. I can just put the inverse function to the left, and I know that they're going to cancel each other out. I'll just get whatever the number was. Okay, but how do I compute the sine? Well, sine is the opposite over the hypotenuse. The opposite over the hypotenuse should be x over 5. Again, I'm just going to label this with an x and this with a 5. X over 5. I can now use the Pythagorean theorem to get the third side. I take 5 squared, which is 25, minus x squared, and then I take the square root. Okay, it looks a little more complicated. These aren't numbers, but I can play all the same games. Like, let's say I wanted to know, I don't know, say the tangent of the arc sine of x over 5. So the tangent of the arc sine of x over 5, well, How do you get the tangent? It's the opposite over the adjacent. Okay, the tangent of my angle is opposite, which is x, over the adjacent, which is root 25 minus x squared. Huh. What about another one? You over there. Cosecant. Yes, we can do cosecant. The cosecant of the arcsine of x over 5 equals, okay, cosecant is 1 over sine. Oh, we already knew what the sine was. Sine is x over 5. 1 over sine must be 5 over x. Sweet. Okay, use any of the other trig functions you want, you'll be able to play the same game. Okay, now we can get back to finding that antiderivative. Okay, welcome back. So now that we have a good understanding of how we can play with a trig function of an arctrig function, let's use it in this specific situation where we need to find the cosine of the arcsine of x over 3. All right, so we draw our right triangle. This angle here is our theta, and that's equal to arcsine of x over 3. Okay, since we want the sine of this angle to be x over 3, we need the opposite over the hypotenuse to be x over 3. So I make the opposite x and the hypotenuse 3. All right, apply the Pythagorean theorem to get the third side. This will be 3 squared, which is 9, minus x squared, and then I take a square root. Okay, now I'm trying to compute the cosine of theta. The cosine is going to be the adjacent over the hypotenuse. So it'll be root 9 minus x squared over 3. Cool. Now I can rewrite all of these without any arcsines except for this first one. All right, so we get 9/2. Okay, the theta, that's really just what it is, arcsine of x over 3. Okay, minus, remember, sine of the arcsine. Hey, those just cancel. I get x over 3 times the cosine of the arcsine of x over 3, which again was the adjacent over the hypotenuse. So root 9 minus x squared over 3. Okay, and of course a constant of integration. It may be possible to multiply this 9 in and get rid of these denominators, but I'm not going to worry about that and those little details right now. Okay, here's the takeaway from all this. We took a problem that had nothing to do with trig functions on the surface. But by doing a trig substitution, we were able to pretty quickly get an antiderivative, and then with a little bit of right triangle hocus pocus, convert it back into a form that involved just the x's that we need. Now, what was it that made this all work? Why did I choose 3 sine of theta? Well, it's because of this form, this 9 minus x squared. It's no coincidence that when I squared x, I ended up getting 9 here. Yeah, that matching 9 from this 3. So that's what we're looking to do whenever we have something of the form a squared minus x squared. The substitution I'm going to use is going to be x equals a sine of theta. And the reason why I want to use that is because now a squared minus x squared will become a squared minus a squared sine squared theta. Now I can factor out that a squared, and I have a squared times 1 minus sine squared theta. And just as before, I know that 1 minus sine squared is cosine squared, and so I get a squared cosine squared theta. Okay? So I'm going to use this substitution anytime I see an a squared minus x squared, with one little exception, which is if there's an easier thing to do. Okay, but otherwise, that's the substitution I'm looking to use. Okay? In our next video, we'll look at some other forms, maybe x squared minus a squared or a squared plus x squared, where we can use a slightly different trigonometric substitution but get the same outcome.